We have a remote talk by Sam Lander from the Copernicus Astronomical Center in Warsaw. And Sam's going to tell us about superconductivity in neutron star cores. Please, Sam.
Thanks for that, Bryn. So, good morning to everyone in Seattle, and good evening to me in Warsaw. So first I'd like to say that this should be well within the hour time slot. So if anyone wants to ask a question, please don't hesitate to interrupt. It's for anyone who's given a remote talk before, you'll realize it's very disconcerting to give an uninterrupted monologue for 40 minutes to one's laptop without seeing anyone. So please feel free to break that for me. So I think most of the talks that you've had so far at this workshop have been, well, the ones that haven't been terrestrially focused, have been focused on the neutron superfluid in a neutron star. So I'll be looking at the other superfluid in the neutron star core, which is the proton superconductor. And given that we're not all specialists, well, we don't all work primarily on neutron stars, I'll give a little bit of introduction first. So on the left-hand side of this slide, you see a beautiful image, which is an X-ray image of the Crab Nebula. And so the actual Crab neutron star is the dot right in the middle. And the neutron star itself, and neutron stars themselves, we don't see very well. We certainly can't tunnel into them. What we know about them is essentially based on theory. So, and observationally, most neutron stars are observed through their radio pulsations. So you have a radio signal which is generated somewhere around the magnetic pole, which is shown in the purple wiggly line there. The star typically rotates about a different axis from the magnetic axis. So over time, as it rotates around, that radio beam sweeps through the sky and sweeps past the Earth. So you see this regular pulsing modulated at the spin frequency of the neutron star. So, and for a mature neutron star in the simplest form, forgetting about exotic phases of matter inside, you have a core which is superfluid neutrons in a triplet state, superconducting protons, which are mostly believed to be in the type 2 superconducting state. I'll come back to that in a bit, and normal electrons. And then in the crust, you have a solid ion lattice. The electrons are not bound into, like the ions, into the lattice, and they're free. And then in the inner crust, you have superfluid neutrons, singlet ones this time. And they're not very important for this talk, but obviously they're crucial for glitches, as I'm sure you've heard before. So the point is that nuclear physics tells us about the basic structure of the neutron star. And what we know about terrestrial superfluidity and superconductivity really tells us informs us a lot about what we think we know about neutron star superfluidity and superconductivity. And my talk is focusing on the large-scale consequences for the magnetic field of the fact that the protons in the core are a superconductor. You have this 20-kilometer wide ball of superconductor. And it basically splits into two parts. One is an actual concrete calculation of the magnetic field structure that you get when the core is superconducting as opposed to normal. And the rest is a lot of speculation, basically, but hopefully that will raise some discussion. So just again, to orientate those of us who don't work every day on neutron stars, there are some typical numbers here. So a typical inferred exterior magnetic field for a radio pulsar, so the standard way we observe neutron stars, one infers a value of about 10 to the 11, 10 to the 12 Gauss. And what that means is that we see that radio beam sweeping past the Earth, and we see it sweeping past with some period, which is very stable, but over time, the period lengthens as the star spins down, loses rotational energy. So then if you associate all that rotational energy loss as being due to magnetic dipole radiation, you can then infer what the magnetic field is that would give you that energy loss. And that gives that kind of number. A typical pulsar rotation frequency is between 1 and 10 hertz. So I'm not talking about recycled pulsars, millisecond pulsars. Now I'm thinking about ordinary isolated neutron stars. There's another class of neutron star which are of particular interest to for this talk, and you'll see why because of the numbers, which are the magnetars. And they're the most, well, I guess they harbor the strongest known long-lived magnetic fields in the universe. And their exterior fields are inferred to be about 10 to the 14, 10 to the 15 gas. And then, these are not typically seen in the radio. They're seen through a variety of different X-ray emission, both quiescent and steady and rather violent, which is believed to be powered by huge internal reservoirs of magnetic energy. And they're magnetic powered because their rotation rates are actually generally far slower than those of a typical pulsar. So down to something like 0.1 hertz is typical. What we don't know, well, we can infer an exterior magnetic field. What we don't know is anything about the interior magnetic fields. And in principle, those could be a lot higher than the exterior value. So then, relevance to superfluidity and superconductivity, a few numbers now. So firstly, the critical field for the two critical fields for type 2 superconductivity are both density dependent. So I'm just giving rough numbers here, ignoring that density dependence. So broadly speaking, HC1, the lower critical field, is about 10 to the 15 Gauss, and HC2, the upper critical field, is about 10 to the 16 Gauss. So the relevance of HC1 in a terrestrial superconductor is that if B is below that value, actually you don't get flux tubes. You get all of your magnetic flux is Meissner expelled out from the sample. In neutron stars, it's believed that that expulsion is so slow that even well below HC1, you still get an array of flux tubes. But HC1 does dictate it does give you the magnetic field, the characteristic magnetic field strength along a flux tube. So it is still a relevant number for us. HC2 is the magnetic field above which superconductivity is destroyed. Okay, and when do we get these phases, these two superfluid phases? So the protons start to form Cooper pairs when you drop below a critical temperature of about 10 to the 10 Kelvin. Again, it's density dependent, but this is roughly what it is. And for neutrons, it's about 10 to the 9 Kelvin. So the upshot of this is that given the neutron stars cool very rapidly from their initial temperatures of above 10 to the 11 Kelvin, the core starts to form a superconducting phase after about a year, and the neutron superfluid in the core starts to appear after around 100 years. They have a short phase with normal matter, then proton superconductor, and then later the neutron superfluid joins it. And the interesting thing about magnetic field strengths of magnetars is that they're very much comparable with those two critical fields. So it's quite possible that you could have in a magnetar some regions which are superconducting and some regions which are not, or indeed, if the field strength is high enough in the interior, that superconductivity is completely destroyed. And I'll come back to that at the end.
Sam, can I ask a question?
Yeah, sure.
So,
I'll go back.
In this picture, you're assuming that it always forms a type 2 superconductor. How much do we know about that? I mean, do you not be forming type 1 superconductor further deeper in the core or something?
Sufficiently deep in the core you could do, although I think because the constraint that the maximum mass of an equation of state has to generate a maximum mass of 2 solar masses or more, because we've observed such heavy neutron stars, means that the equation of state has to be relatively stiff, and so that there's not that much density, relatively speaking, there's not much density variation in the core. So I think that broadly the type 1 region would come at higher density. So I think that's the observations of heavier neutron stars sort of pushing us towards any region which is type 1 superconducting being much further into the core. But yeah, I mean, one certainly could have an inner core like that. I don't consider it here because the type 1 phase doesn't have a kind of a neat mesoscopic distribution of flux that one can then average to a macroscopic scale. And I think it's not really, no one really is really sure what to do about modeling a type 1 phase. It would have to be some sort of evolutionary calculation. So I guess it's two things. One, I think a lot of the core probably is type 2 superconducting, although there could be type 1 towards the middle. But the other reason is a sort of pragmatic thing of we're not particularly sure what to do with it. But yeah, the phase could indeed be there.
Right. And maybe another question, just to clarify it, or to understand. So you have two critical temperatures, roughly speaking, 10 to the 10 for protons, 10 to the 9 for neutrons. But I mean, how is it modeled? So how even to get these ballparks, critical temperature for these transitions at high chemical potential?
So I'm afraid I couldn't tell you any of the details of it. They come from energy gap calculations about when it's energetically favorable to form a Cooper pair. But to be honest, it's the microphysics which I haven't actually worked on myself. I mean, I can tell you roughly what they look like, but
in some models they're like multiple populations at high chemical potential, and these numbers are taken from there.
Sorry?
There's some model calculations at high chemical potential, and the numbers are taken from those model calculations. Because I mean,
it's a BCS kind of.
BCS, okay. No, sorry, just it's just it's only a factor of 10 between protons and neutrons, and I don't even know where this can come from and to what extent this actually can be close to physics or not, and that's why I was asking which. Okay, thank you.
Okay, I think yeah, it's basic just BCS type gap models. There's some variation. I mean, there isn't sort of precise consensus in the literature about the exact shape of the gap or the exact value, but there's definitely something that separates the two. I don't know if it's relevant that the core neutrons it's a triplet state that you have to form. I think the singlet state in the inner crust, the critical temperature is again around 10 to the 10 Kelvin, like the protons in the core.
So is it the Coulomb that makes proton critical temperature higher than the neutron?
So it's S wave in protons, they have lower density, grain gap is larger. In neutrons, it's P wave, and it's much lower at the higher density. Simply that's the
it's the P wave.
gap.
All right, thanks, Sam.
So the neutron helium-3.
Yeah, but yeah, like I said, so the singlet neutron state, which forms in the crust, that gap sort of peaks around the same critical temperature as the core protons. It's just that the singlet gap for the neutrons drops more or less at the crust core boundary. So then you have to wait for the triplet state. Okay, so what evidence do we have for superfluid and superconducting states inside neutron star cores? Well, the first thing is, it's not evidence, but from what we know from terrestrial theory, if you apply it to neutron star parameters, essentially, you find that neutron stars should quickly be cold enough to host superfluid and superconducting states. And actually, the first work on that was done by Migdal only 2 years after, if I remember right, only 2 years after the classic BCS paper, and about 8 years before neutron stars were actually discovered. So he just sort of taking a star of kind of nuclear density, he found that the critical temperature should be, I think his estimate was 10 to the 10 Kelvin or something. And he rightly inferred that if a neutron star were to exist, it probably would cool below that temperature quite quickly. Then, shortly after neutron stars were discovered, there was a host of theory papers that accompanied that, and the classic one within our field is a Nature letter from 1969 by Bain, Pethick and Pines, which is really still, in some ways, it still describes some of the state of the art within this field. So from the theory side, that was to be expected. From the observational side, the big evidence is pulsar glitches. So the only credible explanation to have a sudden spin-up event in the long-term slowing down of a neutron star is that you have a transfer angular momentum from some hidden component you don't see, which has to be a superfluid, because it has to be able to decouple, back to the crust. And so that doesn't explain the superconductor, although in all of these models, you get the superconductor before the superfluid anyway in the core, and you get one with the other one. There was apparently some evidence from the young neutron star in the center of the Cassiopeia A supernova remnant, which is something like 300 years old. Around 2011, we thought there was evidence that this neutron star was undergoing a really rapid phase of cooling, something like, I think, 10% of its 10% cooling in a matter of years. And that would have been in accordance with the splash of neutrino emission from the onset of neutron superfluidity. When you form Cooper pairs, you get some splash of neutrino emission. And that model requires, though, that your protons were already in a superconducting state to explain the data. So a couple of papers came out in 2011 on that. Unfortunately, 2 years later, there was re-examination of the data, and that temperature drop was not shown to be statistically significant. So that one has gone. On the other hand, I think the expertise or the knowledge we've built up from trying to confront our theory with observations like that, I think will probably come in handy if we have a chance to observe another young cooling neutron star, because that phase should be there somewhere. If we get lucky, and if we get lucky, we can see it. There's some hint that we sort of, if you like, a direct hint of the presence of the superconducting component could come from the largest observed glitches. There's some hint that they can't be glitches that come from the crust alone, and I'll talk about that a bit later. So, if neutron, the big question here for the most substantial calculation for this talk is, if neutron stars have superconducting protons, what's the effect of that on their magnetic fields?
Sam,
so
just a technical thing. Is there any chance on your screen you could move the zoom widget a little bit further down? Does it let you do that?
I would like that, because it's upsetting me as well. I can move it
Sideways, but not down.
How about way at the top?
Yeah, maybe right up at the top.
Yeah, let's try. That's good. Is that less irritating? It's a bit better for me.
Yeah, I think that's okay.
It's upsetting. Maybe this corner's
Yeah, maybe that corner's the best. All right, thanks.
Okay, yeah, thanks. I didn't know I could do that. So this also means I can actually read my slides now.
Okay, that's even better.
So the first thing one thinks of when one thinks of a superconductor is the Meissner effect. So below some critical field strength, magnetic flux is expelled from the superconducting region to the boundaries. So this is still a contentious point, but it's believed that's less relevant in neutron stars, because anything that allows that Meissner expulsion to occur is probably so slow that even below the critical field strength, which is HC1 in this case, the flux is probably quasi-stable. And what that means for a type 2 superconductor is that the magnetic field is quantized into an array of thin flux tubes. So on a large scale, you see some smooth magnetic field, so shown in the left picture. But then if you zoom in, what you see locally on a sort of mesoscopic scale is an array of thin, highly magnetized flux tubes whose characteristic magnetic field strength is about HC1, about 10 to the 15 Gauss, surrounded by regions where there is no magnetic field. So if you like, that's where the Meissner expulsion is. However, virtually all modeling of neutron star magnetic fields just assumes that the core matter is in a normally conducting state. And that's not because we don't believe it's a superconductor, everyone does believe it's a superconductor. It's just that it wasn't clear how to treat the fact that the core state of matter, the core was in the superconducting state. And also, if you have normal matter, you can essentially reappropriate results that have been derived for main sequence stars and just apply them directly to neutron stars. Okay, so if you want to try to model a magnetic field in a superconducting neutron star, a natural place to start is to assume that magnetic field is in a dynamical equilibrium. And that's because a mature neutron star has no mechanism for regenerating magnetic field. The sun is continuously regenerating magnetic field, and it doesn't. So yeah, the sun, for example, continuously regenerates magnetic field, and many main sequence stars do that. There is no such mechanism in a neutron star, so the fact that they have strong, long-lived magnetic fields, it means they must be in some sort of steady state. There's no option of destroying the magnetic field because there's no way to regenerate it.
Well, how do you know there's no dynamo?
Sorry?
How do you know there's no dynamo?
It's a pretty. So there's no physics to drive it really. I mean, in the sun, you have this hot convective region in the outer region, and convection is a key ingredient for a mean field dynamo. So you have usually a combination of convection and differential rotation, for example. A neutron star is essentially a zero temperature object, and it has a crust on top of it as well. And I think there's no. You could maybe sustain some very slight differential rotation, but I think you don't have any of the ingredients that you need to generate or regenerate a substantial magnetic field. Right at the birth you do, and it's believed that the strongest magnetic fields, or maybe all neutron star magnetic fields, are amplified by some dynamo action, but that shuts off a matter of seconds after birth.
Generally, it's stably stratified. So
What?
it's stably stratified as well, so you can't really get the thermal or compositional gradients. Possible.
Yeah, that's right. Okay, so yeah, if you don't have any way to regenerate the field, you better have a field which is stable and is not going to go anywhere. So a dynamical equilibrium is the simplest way to get that. So in this modeling, I'll also assume the core neutrons are superfluid, although actually it doesn't really have much effect on the magnetic field structure. I'll assume that the elastic crust of the star is unstressed, which is not reasonable, but it's sort of necessary within this calculation. This is a fluid equilibrium calculation. If you allow the crust to sustain stresses, you can sort of, in the crustal region, you can kind of balance any kind of field configuration. You can't really, and the actual stresses that you get there would depend on the seismic history of the crust and everything else. So it's just a different kind of calculation. It's not, you can't then sensibly tackle that with an equilibrium calculation. So it's a sort of necessary evil. And it mostly here I'm ignoring rotation, but it's trivial to put it back in. You just replace the phi, which means gravitational potential here. You place that with gravitational potential plus a rotational potential, and it just goes in the same way as long as your rotation is rigid or follows the contours of the magnetic field. So you have one Euler equation for each of the two fluids. So there's one for the protons, the gradient of the chemical potential balanced by the gravitational potential, and then there's the magnetic force term, and the neutron one, which is the same but without the magnetic force term. And in this work, I assume a double polytrope, which means that each of the two fluids obeys its own polytropic relation, although they don't have to be the same polytropic relation. So the overall star is not actually barotropic. And the two fluids are essentially uncoupled. They're only very weakly coupled because they sit in the same gravitational potential. And regardless of whether your star's normally or superconducting, you have to satisfy div B is 0. So the bit that changes is that F mag, the magnetic force. So before I move on to that, I'll just pause to talk about the neutrons for a second. So the protons are my problem here. The large scale effect of the neutron vortices is, for this problem, kind of trivial. We assume that we know the local magnitude and direction of the rotation. And for rigid rotation, for example, it's the equation you see there. That gives you the rotational potential. And you really just demand that whatever your lattice of vortices looks like on a mesoscopic scale, it averages to give the macroscopic force that you want. And so the simplest geometry that gives you that is an array of vertical lines. And whilst it's true that neutron vortices are probably pretty rigid, I would doubt in reality that over the whole 20 kilometers that they would stretch from one end of the crust to the other end, I would doubt they would really be completely straight, and neglecting curvature is probably unwise. And as you all know, of course, they could be subjected to turbulence as well. So just because we've prescribed what's happening on the macroscopic scale, I wouldn't be sure that we know what's happening on a mesoscopic scale. It doesn't matter for the equilibrium calculation, but it could affect core pinning. I'll talk about later. So then back to the protons. So for the protons and for the magnetic field, we don't know a priori neither the magnitude nor the direction of B. But because we're assuming a type 2 superconductor, we're assuming that we have a regular lattice of flux tubes, and that means we can take a kind of smooth average for macroscopic scales. And if we do that, we get basically a superconducting version of the Lorentz force. And it was first derived from some thermodynamic arguments in the 70s, and it was re-derived in this smooth averaging procedure by Labadakis, Anderson, and Samuelson in 2011. So just to compare the two, so on the left we see the familiar Lorentz force, and I'll show in a minute what we can do with that to actually produce equilibrium configurations. On the right is what happens if you have a type 2 superconductor. So I guess it's a bit more complicated. Maybe the two main things to note here are that there are two different magnetic fields in here. There's the B, which is like the B on the left, but there's also an HC1, which is a magnetic field with a characteristic value of around 10 to the 15 Gauss. And you also see that B appears in this scalar form here on the right-hand side, which is going to cause some trouble later as well. So firstly, looking at what happens if you have normal protons or normal matter in general. So there's a couple of tricks here to get to a point where you can actually solve the equilibrium equations. Firstly, the fact that the divergence of B is 0 means that your ostensibly 3D magnetic field only actually has 2 degrees of freedom. So if you now assume also that the star is axisymmetric, intuitively, it should be possible to express everything to do with the magnetic field in terms of a single scalar variable. And yeah, and this is this stream function U. So firstly, you decompose the magnetic field in this form, and you can show that that's in the equation there, and you can show easily that gives divergence of B is 0. This is in cylindrical coordinates, by the way, so this var P is the cylindrical radius. Basically, after a number of algebraic tricks, you arrive at an equation, this PDE in the green box, which is called the Grad-Shafranov equation, after 2 of the 3 authors who first arrived at it in 1958. I don't know where Rubin went. So on the left-hand side, you have an operator which is almost a Laplacian, but the sign on the last term is wrong. And on the right-hand side, you have 2 terms. The first one is related to the Lorentz force, magnetic force, as shown there. And the second term is related to the toroidal field component. So U is sort of the poloidal field stream function. And the toroidal field is also dependent on that poloidal field stream function. And the peculiar thing about it is that this u appears on both sides of the equation, which is not what we're used to seeing when solving differential equations. And that's a bit problematic, but one natural way to try and solve it is with iterative methods. So you essentially numerically iterate both sides of the equation until you get to a solution where each side agrees with the other one. So actually you can do more or less the same thing if you have a type 2 superconductor. Most of the steps work and you just have to redefine a few things. But the magnetic force function, which is defined here, so the gradient of, is defined such that the gradient of m is this magnetic force divided by rho. That is no longer a function of u, and that's a bit problematic. And I'm going to jump back again, sorry. And this scalar b, what I said was going to come back to bite us, comes back to bite us at this point. So the magnetic field magnitude b, it appears explicitly as well now, which it didn't in the previous one. So this is the equivalent of the Gauss equation for a type 2 superconductor. And the terms in red are basically the ones which are different from the normal case. So there's this capital pi is as defined there. The y function is almost the same as the magnetic force scalar function, but not quite. And again, the f basically describes what the toroidal component does here. I'm about to go on some results. Before I do, I'll just give you a sketch of the geometry so you know what to expect. So again, we have a crustal region where the matter is normal, and a core region where it's superconducting. The poloidal field lines are parallel to the screen, the ones shown in blue here. The toroidal field lines, so any given toroidal field line is circular, and it's perpendicular to the screen. It cuts through the screen in 2 points, as shown here on the left-hand side. And if you look down from the pole instead of from this view, they're circular. And a peculiarity about axisymmetry is that the region in which the toroidal field is able to exist is demarcated by a poloidal field line. So the toroidal field sits inside a poloidal field line neatly like that. And that comes from the fact that there's this f equals f of u function which describes the toroidal field. So then the final thing is if you, the vector, I didn't mean vector product, I meant vector sum, sorry. The vector sum of the poloidal and the toroidal components, if you look at what's happening in this region here, you have a poloidal field going around like this, and then you have a toroidal field which is moving in and out of the board. So if you add those two things together, you get a poloidal field line which looks like this joined up slinky. So this is one half of it, and then it goes around the back and joins up there. And that's the reason this is often called a twisted torus region. And again, that will matter for core pinning a bit later. So before we come on to my results from solving this equation.
Can I ask a question here?
Yeah, sure.
It's not entirely clear to me. The flux tubes, would they wrap around in order to form the poloidal field? Or is the result only of averaging?
Yeah, well, I think I'm right in saying this. I mean, I think the flux tubes follow field lines. So I think you can indeed think of this slinky thing as being what one flux tube would look like in that region of the star.
It won't be necessarily parallel to the axis of symmetry, right? Flux tube, which will deform elliptical shapes, correct?
Yeah, they don't have to be. They don't have to be parallel to the magnetic field symmetry axis. No, I mean, if I weren't working in axisymmetry, they wouldn't need to be. They wouldn't need any kind of symmetry like that at all. But yeah, they follow at least by assumption, they follow the direction of the field lines.
But Sam, this is still, this is a fluid calculation, right? So that line you've drawn is the macroscopic field. So I guess you would average over a bunch of flux tubes, right? So on average, I guess they have to point in that direction and do that kind of slinky thing. But
Absolutely. Yeah.
on a smaller scale, you could have all kinds of twisting and stuff. Just it should average out to zero when you.
That's what I'm trying to understand. What happens on the microscopic scale?
Is that not true? That on the microscopic scale, there could be a lot more going on. It just has to average out when you do your fluid, like, you know, define your magnetic field in the fluid element.
So yeah, mathematically, yeah, I don't know of a physical reason why it should have a lot of small scale structure. And actually, if you produce a magnetic field with a lot of small scale structure, it's more liable to be smoothed out again by ohmic diffusion. I mean, you have it's a very highly conducting medium, but if you put too much small scale magnetic field structure, I think that's liable to be dissipated. So yeah, I don't know, to be honest. Yeah, certainly the safe thing to say is that this represents what the average field does. But I don't have any convincing arguments for why the local field should be so sort of tangled up. But yeah, it's allowed to be, in a sense. I don't know physically why it would be, but yeah, it's allowed to be.
After producing this coarse graining, you see, you obtain this type of solutions which might not be related to the microscopic structure. I don't know, is that possible?
Couldn't quite hear that bit, so I could.
You'd have to speak a bit louder.
Oh, I'm sorry. You see, the fact you see that the flux fields, I mean the magnetic field lines, you see, they'll wrap around. You see, and have this colloidal structure.
Yeah.
Could be an artifact of the macroscopic equation which you wrote, because you neglected certain microscopic terms.
Can't think of anything obvious that I've neglected. I mean, the only actual
Well, you produce an
obvious neglected term is the London field, but that's something like 10 to the minus 2 Gauss. So
I don't know exactly what happens. We didn't follow the derivation exactly, but we see only final result. So it could be that some small terms, you see, they have an effect which is neglected here.
yeah, so I think that's right. I mean, I think the physics that yeah, it's a little bit like the vortex case where you know what things look like on a macroscopic scale, although there's different microscopic setups that can give you that averaging. I don't know much physics that would give you a very kind of, I can't think of anything obvious that would give you a very tortured looking local magnetic field that would be sustained. But that's not to say there isn't any. I'm just saying that, yeah, I don't personally know what physics would give you some very, very tangled local field. But it's for sure it's completely possible, and it's certainly not ruled out by this macroscopic calculation.
Okay, thank you.
But yeah, I think like Bryn said, the safe thing is to regard this as being an average of what, you know, some number of flux tubes, neighboring flux tubes, look like on a macroscopic scale. So you can get some simpler solutions without actually solving, come back to it again for a second, without actually solving this equation directly. And the first paper with any kind of equilibrium for a superconducting star was actually really decades ahead of its time, and it was published in a rather obscure journal, and it's been overlooked, I guess, for that reason. So Roberts in 1981 assumed an incompressible star, and he used that magnetic force that I showed earlier. He got it from Easton and Pethick, which had been published 4 years earlier. And from some geometric arguments, he was able to produce this magnetic field, which is shown here. So, and this is just, there is no crust here. This is just a type 2 superconducting incompressible fluid. And that was actually extended to compressible stars by Henriksen and Wasserman a few years ago. And it looks fairly similar. I think their field lines are a bit more straight. And you notice actually none of them close within the star. You can also do results for a purely toroidal field where you don't actually need this equation. This equation describes a colloidal field or a colloidal plus toroidal field. There's a separate case which is a purely toroidal field where the magnetic field essentially just depends on the density. The magnitude just depends on the density, and the direction, as I said before, we know is just into and out of the board. And then that's been done by, again, Ira Wasserman with Aggun in 2008, and some work that I've done with Neil Sanderson and Kostas Kalabadakis several years ago now. And okay, this is an example of what it looks like. So this is now the magnitude of the toroidal field, and as I said, the direction is into the board. But there's clearly reasons to consider the linked toroidal magnetic field. Firstly, it's the most general case, and secondly, as I'll come back to in a minute, you probably need that to get this mysterious core pin that I keep talking about but don't explain. So I'll come back to that later. But to get there, we need to solve this analog of the Grad-Shafarov equation, but it's more difficult than the other equation. And it's essentially because this pi variable, which depends on the magnitude of B, well, the magnitude of B depends on the gradient of U, magnitude of the gradient of U. And in evaluating that, in having to take a derivative before to plug in as a source term for your differential equation, it makes the numerical iterative procedure just much less stable. So, but, well, I got there in the end. And this is what the magnetic field looks like. So this is, so let's start. So what you're looking at here is the color scale shows the magnitude of the poloidal magnetic field. This is purely poloidal. And then the black lines show the direction. So they don't have arrows on the end, but this is just field lines. The stellar surface is at a radius of 1, and the cross-core boundary, which is not shown, is at a radius of 0.9, but you can see features of the cross-core boundary. And so maybe I'll start actually with the normal case. So the green box shows what you get in the same case for normally conducting matter, not superconducting matter. So you get a poloidal field which is strongest towards the center, and it has these characteristic loops, and the field goes to 0 in some region here. And the point is with this, if I show you the same plot for 10 to the 15 Gauss, or 10 to the 10 Gauss, or 10 to the 1 Gauss, it looks identical, only the magnitude varies. It's sort of scale independent because there is no characteristic magnetic field strength built into the Lorentz force. It's just the curl of B cross B. In the superconducting force, though, if you'll forgive me for jumping back again. So I mentioned before, there is now a magnetic field with a characteristic strength of 10 to the 15 Gauss sitting in that force. And so in retrospect, it's not surprising that the results you get are qualitatively different at different field strengths. So broadly speaking, this is about 10 to the 15 Gauss on the left, about 10 to the 14 Gauss in the middle, and about 10 to the 13 Gauss on the right. So you see that region of closed field lines gets pushed out, and you get rather sharp features of the cross-core boundary. And actually, you can see some agreement between this right-hand result and the previous results of Roberts and Henriksen and Wasserman. So if you just look at the core region, you see there's no closed field lines at all now. And that's, I would say, reassuringly similar to the plot from the Roberts paper here. So this is poloidal fields, but now I have the technology to do poloidal plus toroidal fields, so let's look at those. So now the color scale shows the magnitude of the toroidal field. The black lines are still the poloidal field lines. And again, if you look at the normal magnetic field, sorry, the normally conducting case, whatever field strength you're at, the plot looks kind of the same. But now with the same setup, again, average magnetic field of 10 to the 15 Gauss on the left-hand side, 10 to the 14 in the middle, and 10 to the 13 on the right, you see that that region of toroidal field, which has to sit within a poloidal field line, as dictated by axisymmetry, that toroidal field gets pushed out towards the crust. So again, there's qualitative differences from the normally conducting case. And actually, I'll point out at this point that it makes me personally rather uneasy when I read solo papers based on, you know, numerical projects. One always wonders how much to trust them. I have to say that this code of mine was independently reconstructed by a master's student in Thessaloniki, Kostas Panavanidis, with his supervisor Nick Sterioulis, about a year or two later, and the results are quite similar. And in the end, we wrote a collaborative paper on that. So there is, you know, these are reasonably robust, I would say. So finally, at the very end of the talk, I get back to the thing which I've been promising all along, which is core pinning. So what is it? So entrainment effectively magnetizes the neutron vortices, which neutrons are neutral, they should have a magnetic field, but through entrainment, they have an effective B neutron. And, well, the classic reference on that in relation to neutron star rotational properties is Alpar, Langer and Sauls from 1984. Actually, David Zadrakian was working on this back in the mid-70s and the early 80s as well, although that result's fallen by the wayside a bit. But I think he was the first one to get there. So we now have a magnetic field on the protons and a magnetic field on the neutrons. And you can find the energy of a vortex-fluxtube interaction, so an intersection between a vortex and a flux tube, from energy expansion, which is basically directly from Ginzburg, the Ginzburg-Landau expansion. And it's claimed, I haven't quite understood why, and it's not very clear in the literature, but it's claimed that the main part of that energy is essentially a term which is a geometric term, which is the neutron magnetic field dotted with a proton magnetic field. And so what that means is that for a neutron vortex to get past, for a rotational vortex, a neutron vortex to get past a flux tube, to cut through it or to push past it, it has to overcome some energy barrier, which is proportional to this. But it won't always encounter that energy barrier. It depends on the field geometry. So if you look here, so the red lines here are the flux tubes. Again, they're the field lines. So for now I'm forgetting about any chance that there's different localized structure of the magnetic field. I'm just assuming that this represents a flux tube. And then the blue lines are the neutron vortices, and they're curved kind of for convenience for the plot. So a neutron vortex moves out over time as the star spins down. So to adapt to the new lower rotation rate, the neutron vortices move out gradually, but they encounter flux tubes. And depending on the way the flux tube they encounter, the geometry of that flux tube, they may or may not be able to freely get past it. So if you hopefully can picture what's happening here, the vortex can weave past a poloidal flux tube, at least in this geometry. So the idea is your vortex starts here. Sure, if it crashes directly into the flux tube, it would encounter the maximum possible energy penalty, because that would be the maximum scalar product. But it's really easy for it to just move slightly around it instead and just miss it completely. So it avoids it, so it has no energy penalty. It can also cut straight through a toroidal flux tube. The vortex starts here, and if it cuts through a toroidal flux tube, it hits it at a right angle, so then the scalar product is 0. But the one thing it definitely can't get past is this slinky-like geometry, this colloidal toroidal twisted torus flux tube. There it has to get stuck somewhere. So the idea is that means that causes some sort of hold up in how readily the neutron vortices can move outwards in the core. And yeah, this comes back to a point that we've mentioned earlier. It's not very clear how to do that averaging to get the macroscopic effect of this, and something that a few of us have been working on for a little while, and nothing's published because we have some conceptual uncertainties about this still. But yeah, whether you have some sort of localized turbulence or localized small scale structure in the flux tube or the vortex could seriously affect just how big or small this energy penalty is for having to cut through. And furthermore, this isn't. Yeah, Bryn?
To go back to what Aurel was saying. I mean, your cases 1 and 2, they kind of rely on thinking of these, the macroscopic field, and then saying, well, I've had all these flux tubes like this, but like case 1, I guess in reality, there's so many more flux tubes than neutron vortices, and their tension is so much smaller that I would expect that it can't really just go through this forest of flux tubes. I mean, the cross section for actually having something happen must be quite high, right?
Smaller than a swamp.
Yeah, and they do, and that on average they're straight, but they're not really. I mean, the neutron vortices are much straighter, so
yeah,
I think they can really dodge through. And also, too, right? You still have that's the magnetic overlap. You would still have some energy gain just from the overlap of condensation energy. So it's not really complete. So you can't cut like that just for free. So I guess those cases are probably quite idealized, right?
So the condensation energy overlap thing, this is something it's claimed in a few places in the literature is subdominant to that interaction energy I've shown there. But to be honest, I haven't found anyone that's actually explained why. And there's a series of private communications, which is kind of frustrating. But yeah, for the sorry?
I remember seeing the numbers, and it kind of is, but it's still relevant, right? I mean, if the other process is going to 0, then that takes over.
Sure. But I think what you said is right, that the problem is one can get a picture of what's happening on the level of an interaction between one flux tube and one vortex locally.
Right.
And in that case, I think the pictures 1, 2, and 3 work. But the problem is, this isn't a vortex whose total length is 1 femtometer or whatever. It's a vortex that, in principle, is 20 kilometers long. So, yeah, there is definitely. Well, okay, you also want to elaborate on this. You know the reason we haven't yet, managed to sort of finish this. Yeah, it's really not clear how to go from those local ideas to do the averaging, if you like, in the right way to see what the macroscopic effect of that would be. And furthermore, even if we could do it for this case, this is an idealized case where you have an aligned rotator. So the rotation axis and the magnetic axis are the same. And we know the pulsars, at least that's not the case. Otherwise we wouldn't get the pulsed radio emission. So then, even if one has a handle on how the problem works in the aligned rotator case, one then wants to tilt the whole vortex array with respect to the flux tubes and deal with that. So it's hard. But on the other hand, there's good motivation for trying to do it. And one of those is, it comes back to calculations from Nicolas Chamel from, well, the early 2010s, where he argued that essentially the neutron, this angular momentum reservoir that one appeals to explain glitches from the crustal superfluid is not as big as you would think it is. So that there's the effect of entrainment drastically reduces how big a glitch you should be able to get from the crustal superfluid. And that suggests that you can't explain the largest glitches with superfluid that is in the crust alone. So then you go looking somewhere else for some extra angular momentum. And so you look at the core, but the core is clearly far too much. You would, in principle, if you can have angular momentum reservoir in the whole core, you could expect glitches which are vastly larger than we see. And the reality is it's a factor of, 2 or something we want to explain. We want a factor of 2 increase, say. And core pinning is appealing here because you get a modest increase in the angular momentum reservoir, and you get it in a very distinct region, which is this toroidal, this mixed colloidal toroidal region out near the cross-core boundary. That's the shaded pinkish area there. But if you believe the equilibrium results, that requires that the internal magnetic field is greater than about 10 to the 14 Gauss, because if you recall what's happening here, once you get below about 10 to the 13 Gauss, there is no core pinning region. Again, assuming that there's no pinning when you have a purely colloidal field, which is the case in the core here. If you need that colloidal toroidal mixed linked region, you need the magnetic field geometry to look like this and extend into the core. So that's interesting because it gives this provocative idea that is it the case for all big glitches that the internal magnetic field is indeed that strong? Because the external field is more like 10 to the 11, 10 to the 12 Gauss for those objects. I don't know. One of the big implications is in field evolution, and magnetic field evolution in the core is a very contentious issue still, and it could easily have written a whole talk on that instead. But core pinning leads to a field evolution mechanism, which is a coupling between the rotational and the magnetic evolution. And it's basically the same plot that you've seen before. As the star spins down, the vortices move outwards. If there's an energy penalty for cutting through them, maybe they drag the flux tubes with them instead. So then the vortices are moving outwards, and the flux tubes are moving outwards with them. So the magnetic flux, which is in the flux tubes, is being dragged out towards the cross-core boundary. So what happens then? So it could be dissipated as heat. It could somehow boost the crustal field and excite crustal field evolution processes, which are better understood. Or it could cause the buildup of stresses which break the crust and produce well, violent energetic activity, like the activity we see from magnetars, or in fact the activity we've seen also coincident with a few glitches recently. So there's a few big reasons to try and understand core pinning. So to summarize what this talk was trying to show you. So the more concrete things, there's a first set of magnetic field solutions for a neutron star when the core is superconducting. And there's some hints that there's interesting differences in the qualitative geometry of the magnetic field above and below about 10 to the 14 Gauss inside the star. So that's the things done right. And then there's much more uncertainty, of course, afterwards. The core might not all be superconducting, or it might not all be type 2 superconducting. I have no idea how to deal with the type 1 region. Like I said, you don't have that local ordered structure of flux tubes that you can average over. In the region between HC1 and HC2, which is actually the region where, formally speaking, the flux tubes are stable, the flux tubes are also so tightly packed that there should be interactions between them, and that's not covered by these models. And that could be relevant for magnetars, if magnetars are not actually above that value completely, for example, in some regions. There's big issues about how one treats the cross-core boundary, the evolution of this system, and yeah, like I said before, type 1 superconductivity. And there's also, I think, a fundamental issue here that we don't normally talk about, which is that this Abrikosov lattice, this flux tube lattice that we have, And this model of interaction energy that we have comes from Ginzburg-Landau theory, which is reliable near the critical temperature, but neutron stars have, all observed neutron stars are well below that temperature, and they've dropped below that. Well, for the critical temperature for protons, they've dropped below that after a year or so, a few years of life. So I've no idea how one treats that, but it certainly means that we have to be we have to tread a little bit carefully with how many of these results we take as, gospel truth. So then some speculation. It would be wonderful if we could link the physics of core pinning with the observations of large glitches, although there's obviously work to be done there. Maybe objects with large glitches, that is some indication that they have interior fields much stronger than their exterior fields. And that maybe the core pinning, the evolution that's driven by this core pinning effect, could be powering some of the high energy activity that we see in some neutron stars and magnetars. So thanks for listening, and thanks for interrupting especially.
Okay, other questions for Sam?
So I had one question. So Sam, do you have some sort of an estimate as to the competition between the pinning force, which is due to the B and U dot B P term, and the Magnus force for a typical velocity jump? Let's say for a Vela per star or something. I mean,
I couldn't. So actually, some of the conceptual issues that Bryn raised have prevented us from getting to that point. I can refer you to. There is a bit of work on this topic, which I would say is much more qualitative rather than quantitative, but explores a lot of these ideas by Gügüd Sinoglu and Alpar. I'm just going to find. I've got the name written down somewhere. My Turkish pronunciation isn't good enough. So yeah, they have a series of papers, but possibly that one, I think, has some estimates. I can't remember the conclusions. I think it's also complicated because they assert that the vortices should be in this sort of creep regime where they can, in principle, sort of slowly get through the flux tubes anyway. But yeah, I don't have the numbers off the top of my head, but I think that's probably maybe the best recent reference to look at for that.
okay.
So probably can't be more precise.
You make a lot of assumptions, just do the straight calculation and you average everything and hope that it sums up nicely. You can build up lags that are quite large, so you can comfortably accommodate glitches, but of course you have to make a lot of assumptions to get there. Sam said it's unclear how many of these actually hold. Oh. Yeah.
So, I don't know if I understand correctly. So, you mean in toroidal region, we have many vortex rings or protons in maybe. So we had. I think you showed some picture that in a toroidal region, toroidal is.
I'll try and find the picture. This one?
That one?
Maybe, yeah. You can go over there. I think you.
Yeah, I guess if you go there, you can move with your hands.
Yeah, you can.
Look at the camera on the laptop.
Yeah. Okay. So so you mean this in this toroidal region, flux tubes forms rings, many rings?
Yes, in principle. I mean, subject to this discussion we had about whether you should really regard this as being really what a single flux tube looks like, or what some sort of average of a few flux tubes looks like. But yes, yeah, it would. In principle, it's.
So that's like a slinky kind of thing, right? So
yeah.
it keeps going, right? It's not
And
Yes, and that's half of it. Yeah.
so in this workshop, I learned that the number of flux tubes is much larger than vortex tubes. So there are many rings, kind of rings, and you mean pinning occurs in this toroidal?
Exactly. Yeah. So again, forgetting about all these other things we're discussing about whether you can really have a 20-kilometer vortex that can completely swerve past a series of flux tubes. Forgetting about that and just looking at what happens on a local level, this region is the region that a vortex definitely cannot get past in any case. Even if it can swerve past poloidal field, and even if it can cut perpendicularly through toroidal field, it can't get past this kind of coiled region. It will always hit at some kind of angle, and so there will always be an energy penalty of that form. So yeah, that's what I'm saying.
That's of course what it does is bend so that it can cut at the preferred angle, right?
Well, I don't think you can actually. You could sort of no. I don't think you can do that in that region. You can sort of. I mean, you have to. Well, I don't know. Maybe you can find some really tortured way where it cuts everywhere at 90 degrees. But I think that's pretty. That's pretty hard to do.
I thought of it. I guess you have to compare the tension to the actual cutting penalty in energy.
Yeah.
All right. Any other questions? Rena, do you have a question?
Yeah, I'm not actually seeing why it can't get by the twisted flux tube region with just a 90-degree cut.
So again, maybe if you like I said, like Brim was saying, if you allow the vortex to bend enough, or the flux tube to bend enough, maybe you can find a way around it. But if you look at, it's a bit hard to say because it's sort of appealing to how one sees the geometry in one's head, and maybe I see it in a different way. But looking at the number 3 there, if the straight vortex is moving outwards through that slinky region,
Right.
it will not hit. It certainly can't swerve past like in number 1, but it won't hit everywhere at 90 degrees. It will always, and it's not one slinky one. I mean, there's a whole. This is a whole mass of nested slinkies.
Okay, maybe that's the problem, because I think with one slinky it can go through just fine. It goes in between 2 coils from the inside, then it crosses the coil.
But
perpendicular.
it has to bend first before it crosses.
It has to bend, yeah.
Crossing is 90 degrees.
Yeah.
That's
So
it.
he's assuming that it's
But I think
perfectly
it
rigid.
crosses at the point right at the bottom, which is 90 degrees to the vortex.
You just have
Oh
to,
yeah, you're right.
Right?
not
So
to
it
go
goes
straight out.
So I guess yes. I guess if you're yeah. So
Come
I guess
in,
Dave's
go like this,
assuming that
then
it
go
goes
out.
straight out and it can't kind of weave up.
Yeah.
But this
Yeah, I agree.
this number 3 is not a pure poloidal or a pure toroidal geometry. It's this vector sum, so it's not.
But the
So it would naturally hit the slinky at some angle which is neither 0 nor 90 degrees. So I think even in that case, I don't think you could get through. But for sure, in nested slinkies, even if you hit one of the slinkies at 90 degrees, you'll hit the next one in at 89 degrees or whatever else.
Because with one, you're right. Yeah,
Right.
you can always find
Okay,
that place
okay,
and
okay.
just go through. Michael?
Do you have anything to say about helicity and generation of fields and stuff like that? Does that play a role here?
So the only thing I have to say about that is that within this this kind of interpretation is a kind of a neat thing that the pinning. Well, I don't know if you can relate how much pinning you get with how much helicity you have, but the 2 zero helicity configurations are the 2 ones that you can get through without an energy penalty, and only in the region non-zero helicity do you get stuck? I'm not sure if there's anything more profound than that, but that would be kind of nice if one could actually, if one could sort of relate how much pinning you get with the helicity, but other than that, I don't really have anything very profound to say. No.
Right, any other questions? If not, let's thank Sam again. Thank you, Sam.
Cheers, Saprin.
Good night.